The James Webb Space Telescope has uncovered something truly remarkable: rays of light that appear to radiate from an urban center, shining from a location light years away. This discovery has rekindled interest in the possibility of life on other planets. The telescope focused its attention on Proxima Centauri, the closest exoplanet to our solar system, and observed odd, bright flashes of light that may be signals from an alien civilization. Scientists and everyday people have been fascinated with the idea of life beyond Earth for years. Any indication of its presence sparks great enthusiasm, but a pivotal moment came when the James Webb Space Telescope presented clear proof indicating the existence of life somewhere in space. While scanning the depths of the cosmos, this powerful telescope discovered an extraordinary event on an exoplanet located far away. It detected lights that resembled extraterrestrial city designs, suggesting the possibility that an alien metropolis might exist on that distant planet. This concept has produced significant curiosity and excitement in the scientific community because it could be the breakthrough they have long anticipated. It suggests the existence of functioning, intelligent civilizations. In a way, we are only beginning to investigate these lights, which resemble those of a large city. Located for light years away, NASA engineers are amazed and perplexed by how long these lights may have appeared in space, waiting for our technology to progress to a point where we could detect them. David Kipping, an astronomer at Columbia University, has written about the planet where these lights were found. Unlike the majority of rocky planets, which absorb sunlight and emit energy as infrared radiation, this exoplanet behaves differently because of its unique relationship with its star, Proxima Centauri. This discovery, made by the James Webb Space Telescope, demonstrates the telescope's crucial function and capacity to capture infrared wavelengths, which was essential in identifying the unusual behavior of Proxima Centauri b. This is crucial for understanding the planet's atmospheric conditions. Researchers are planning to continue using the telescope to study the atmosphere of this planet in greater detail, hoping to investigate the possibility of habitability. The James Webb Space Telescope is particularly sensitive to infrared light, allowing it to observe what happens on Proxima Centauri b even during the night. Many telescopes struggle to detect faint light in the vast darkness of space, but the Webb telescope shines in picking up even the faintest glimmers. This makes it an ideal tool to confirm if the alleged city lights on the dark side of Proxima Centauri b are indeed real. The telescope can detect artificial light in space, provided it falls within a very specific frequency range, much narrower than the light emitted by regular stars. Proxima Centauri b has a dynamic interaction with its star, which significantly influences its surroundings. Like many planets that orbit stars, it captures a lot of energy from Proxima Centauri. As the planet revolves around the star, it goes through day and night cycles similar to Earth, with cooler daytime temperatures and even colder temperatures at night. The range of Proxima Centauri b's temperatures is vast, primarily because of its composition. For example, if the planet lacks an atmosphere, the temperature difference between day and night would be extreme hot on one side and frigid on the other. This dramatic thermal fluctuation is an important subject for astronomers as it provides useful information about Proxima Centauri b's atmospheric makeup. The James Webb Space Telescope, with its aptitude for infrared imaging, is able to thoroughly investigate the planet's thermal emissions, offering insights into its atmospheric properties. The telescope's orbit around Earth coincides with Proxima Centauri b's orbital period, enabling scientists to make in-depth observations of its day-night cycles every 11 Earth days. The next step will be a chemical analysis of Proxima Centauri b's atmospheric composition to determine if it could support life. Detecting elements like methane, water vapor, and oxygen would indicate the planet's potential for life. This would entail studying the light passing through the planet's atmosphere, a difficult procedure. While the James Webb Space Telescope is excellent for describing the atmospheres of planets, it is primarily designed for other tasks. Its expertise lies in analyzing carbon dioxide, water vapor, methane, and other compounds. But it is less effective at detecting free oxygen, an important indicator of life. Nonetheless, the telescope can search for other key indicators, like ozone, which signals a healthy atmosphere. As scientists analyze the collected data, the James Webb Space Telescope's observations in the hunt for distant worlds continue. We are getting closer to answering the question of whether we are alone in the universe. It's important to note that the James Webb Space Telescope can only observe a limited number of exoplanets. For more in-depth examinations of planetary atmospheres, astronomers will rely on ground-based observatories like the Extremely Large Telescope ELT, which will begin operations in 2028. The ELT is intended to provide a more detailed look at the atmospheric structures of exoplanets, offering clearer and more detailed data on their potential to support life. Scientists are eagerly awaiting the launch of future space telescopes. In the meantime, the James Webb Space Telescope remains an invaluable tool for exploring distant exoplanets despite its limitations. The telescope continues to offer important information that could alter our comprehension of what lies beyond our solar system. Researchers have ambitious plans for future space telescopes. They aim to develop technologies that reduce interference from starlight, allowing for better observation of the planets around them, similar to using your hand to block the sun to see more clearly. These upcoming telescopes will be able to focus on the faint light reflected by exoplanets, making it easier to analyze their atmospheres and determine whether they may be able to sustain life. However, this task is far from simple. Stars are incredibly bright, often vastly outshining their surrounding planets. Because of this brightness, it is difficult to detect the planet's faint reflected light, which is essential for studying their characteristics. To address this challenge, scientists are working on several novel methods, one of which involves the utilization of coronagraphs. These devices are positioned to block starlight, enabling clearer observations of exoplanets. Inside telescopes, coronagraphs block out starlight while allowing the planet's light to pass through by carefully arranging the light waves. Coronagraphs can significantly reduce the brightness from the star, facilitating the detection of the dim light from exoplanets. A new, hopeful approach is a significant starshade, a flower-shaped spacecraft positioned tens of thousands of kilometers away from the telescope. The star shade blocks the star's luminance before it reaches the telescope, allowing only the light from exoplanets to get to the instruments. This technique may be especially capable of observing planets within their star's habitable zones, where liquid water and life may be able to exist. However, these advanced technologies require extraordinary precision. For example, the alignment of a starshade must be just right to within a few thousandths of a millimeter in size and distance. Moreover, these innovations must overcome restrictions imposed by space missions, such as the requirement for miniaturization, energy efficiency, and the capacity to withstand harsh conditions. Despite these obstacles, the potential benefits are enormous. Successfully observing and studying the environments of exoplanets could lead to the discovery of biochemical indicators of life, such as water vapor, oxygen, or methane in particular proportions. These molecules might suggest biological processes that indicate life exists beyond Earth. Additionally, researchers are exploring ways to visualize far-off worlds more clearly. Specifically, future telescopes might be equipped with advanced adaptive optics, which adjust for distortions caused by Earth's atmosphere or the telescope's movements, resulting in sharper images. Together with star light blocking technologies, these advances could allow scientists to do more than just detect exoplanets. In addition to mapping their surfaces and investigating their climates, the development of next-generation space telescopes marks significant advancement in our search for answers to one of humanity's most profound questions: are we alone in the universe? By enhancing our capacity to observe distant planets, we are getting closer to finding out if life exists beyond Earth, potentially transforming our comprehension of our place in the universe. The direction of space exploration and the search for extraterrestrial life is advancing at a rate never before seen. As astronomers and scientists delve deeper into the mysteries of distant exoplanets, the James Webb Space Telescope is ushering in a new era of cosmic discovery. It gathers data that assists astronomers in uncovering groundbreaking information regarding the composition and potential habitability of far-off worlds. With each new piece of information, we edge closer to answering the ultimate question: is there life beyond our planet? The discovery of Proxima Centauri IB is just the beginning of what could be a significant turning point in how we approach the study of exoplanets. As the closest star to our solar system, Proxima Centauri has received significant research attention for a long time. However, finding concrete evidence of life, such as signs of artificial light or civilization, has been aspirational. The fact that such light has been detected by the Webb telescope only enhances the hope that one day we may communicate with other intelligent life in the universe. This kind of discovery stimulates scientific interest and public imagination, inspiring new generations to think beyond the confines of Earth. As the James Webb Space Telescope continues its observations, it is not only looking for artificial signals, but also concentrating on planetary atmospheres and the chemicals within them, which might support life. The search for biomarkers, such as carbon dioxide or methane, in the right proportions is essential for understanding whether these planets have the conditions for life. The Webb telescope has the ability to analyze these atmospheric elements in a way that no other telescope has, illuminating the potential of distant worlds to support life similar to that on Earth. One of the most fascinating aspects of Proxima Centauri IB is its location in the habitable zone of its star, where conditions might allow liquid water to exist on its surface. The habitable zone is the region around a star with just the right temperature, neither too hot nor too cold for liquid water to form. This is regarded as an essential factor in determining whether life could exist on a planet, making the discovery of an exoplanet in a star's habitable zone a major target for future missions. In addition to finding life-supporting planets, future space telescopes will also target the complex interactions between exoplanets and their stars. For example, some planets, like Proxima Centauri IB, are tidally locked, meaning one side always faces the star while the other remains in darkness. This may result in extreme temperature differences between the two sides of the planet, which could impact its climate and potential to support life. Understanding these conditions is crucial for astronomers in evaluating the likelihood of habitable environments on exoplanets. The development of technologies for blocking starlight is another important step forward in space exploration. Without the ability to block out starlight, it would be virtually impossible to observe the faint glimmers of light from distant planets. The coronagraph and starshade technologies cited earlier are excellent examples of how scientists are overcoming these challenges. By blocking out the overwhelming brightness of a star, these telescopes can detect the faint light reflected by planets, which could reveal important information about their environments, surfaces, and potential for life. An exciting new development in this field is the concept of direct imaging of exoplanets. With the help of starlight blocking technologies and advanced adaptive optics, astronomers aim to take high-resolution photographs of planets as they orbit their stars. These images would provide not only more comprehensive data on a planet's composition and environment, but also a closer look at surface features such as oceans, continents, or weather patterns. This kind of imaging would represent a giant leap in our ability to study exoplanets and make informed assessments regarding their potential to sustain life. As we move forward in exploring the universe and searching for answers regarding the existence of life beyond Earth, the role of the James Webb Space Telescope and future missions will be indispensable. The telescope's ability to detect faint signals from distant planets, study their environments, and examine their potential for habitability is transforming our understanding of the cosmos. With advancements in technology and a growing body of research, we are on the brink of making discoveries that could reshape our knowledge of life and the cosmos.